Next chapter, force. Now, let us consider these scenarios. First, there is a cart loaded with luggage and which is not moving. In fact, this cart will remain stationary forever unless someone comes and pulls it. When he does it alone, it moves slowly and he appears to be struggling. But when his friends join in, it moves a lot faster and there is no more struggle. Secondly, we have a ball resting on the ground. This too will remain this way forever unless someone kicks it. When it is kicked, the ball rolls on the ground and comes to a stop again after 15 meters. Thirdly, this gentleman throws the ball seemingly upwards, but as it moves, its direction of motion changes continuously. It hits the surface up there and changes the direction, gets into the basket and moves downwards. On hitting the ground, it bounces up and down several times till it comes to rest. Finally, this car driving straight head-on towards what appears to be a metal bar. It crashes against the metal bar and the front part of the car is severely damaged or distorted. In all these cases, we see a change in an object's state of motion or shape. The thing that causes these changes is called force. Defined, a force is a push or a pull on an object. The SI unit of force is called Newton. We cannot see force, but we can feel or see its effects. A force acts in a particular direction and is indicated by an arrow pointing in the direction of action. The four effects of force are what we have just described. It makes a stationary object to move or increases the speed of a moving object. It slows down or stops a moving object. It changes or alters the direction of a moving object. It distorts or changes the shape of an object. Now, does it mean if none of these four things is happening to an object, there is no single force acting on the object? Not at all. As a matter of fact, any object is always under the influence of more than one force. Let's consider the case of the ball. It's resting on the ground and we say it's stationary. Is there any force acting on it? The answer is yes. There are forces acting on this ball. There is the gravitational force which is trying to pull the ball towards the center of the earth. And the ground is exerting an equal force exactly in the opposite direction. We call it the normal force. Because these two forces are balanced, they do not change the position of the object. We say the net force acting on the ball is zero. For the object to move, there has to be a net force. When the ball was kicked, it started moving, and that is because there was another force applied that distorted the balance. Well, there are many types of forces, but let's just look at a few here, starting with the most common one, gravitational force or the force of gravity. Now, if you ask most people out there what gravity is, they will probably tell you that it is the force that pulls objects towards the surface of the earth. Now, from today henceforth, you need to get that idea out of your mind, that gravity has got only to do with the earth and the things near its surface. Yes, it is true that things fall towards the earth due to gravity, but that is just one example of gravitational pull. In fact, gravitational pull exists between any two objects in the universe provided they have mass. Consider any two objects in the universe. They could be planets, humans, animals or whatever, as long as they have mass. Each object is pulling the other towards itself. This attractive force between any two masses in the universe is called the gravitational force. Defined, The gravitational force is the attractive force between any two objects with non-zero mass separated by a distance. It is not just the force the Earth uses to pull the objects towards it, but because all of us live on Earth, most examples for gravitational force will relate to the Earth pulling objects towards it. In the case of the Earth and humans, the Earth is one object and the human is another. They are pulling each other. Having said that, does the apple fall towards the Earth, or does the Earth move towards the apple, or do both move towards each other? Although both apply an equal force to pull each other, the apple accelerates towards the Earth because its mass is much less than that of the Earth. To understand this concept, we need to understand first something called the universal law of gravity. Consider two objects A and B separated by a distance d, which is the distance between their centers. If the mass of A is m1 and that of B is m2, and that m1 is greater than m2, the universal law of gravitation says that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, the force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. These two expressions can be combined into one. So if the mass of any of the object increases, the gravitational force will have more magnitude. And the more the distance between the two objects, the less of the gravitational force. The force of gravity is of monumental importance. It is the force of gravity between the Sun and the planets that keeps the planets in their orbits. It is the force of gravity between the Moon and the Earth that keeps the Moon in its orbit. Next force, tension. Now, this is the pulling force exerted by an elastic object on another, for example a spring or an elastic band. When we stretch a spring by applying a force, the spring in return applies an opposite force to try and restore itself to the original state. The same happens when an elastic rubber band is stretched. It applies a counter force to try and restore itself. In fact, it is this restorative tensional force that allows us to shoot an arrow after stretching the string. The extension of an elastic material is dependent on the force applied. Let's perform an experiment to study the relationship between mass and extension of a spring. First, we measure the length of the spring before any mass is applied. Next, we add a 40-gram mass on the spring and again measure its length. Keep adding more and more mass until we have a table of values. If we plot a graph of mass against extension, it will be a straight line through the origin, indicating mass and extension are directly proportional. Upthrust. Now, if you have ever tried to push an object underwater, you must have felt an upward force pushing on the object. And when you release the object, it bounces back onto the surface. What happens is that the applied force acts in the downward direction, pushing the object down. But the water exerts an upward force on the object, pushing it up. This upward force exerted by water on the object is known as upthrust or buoyant force. All objects floating or submerged in a fluid, including air, experience this upthrust force. So let's perform an experiment to illustrate upthrust in liquids. Suspend a stone from the hook of a spring balance and observe its weight. Slowly immerse the stone into a trough containing water. We notice the spring balance is indicating a lesser weight. When we remove the stone from water, it indicates the initial reading. So there is an apparent loss in weight of the rock. This apparent loss in weight is equal to the upthrust force that the water exerts on the rock. Different fluids have different upthrusts. Next, cohesive and adhesive forces. Consider this demonstration in which drops of water are placed one after the other on the surface of a metallic coin. Evidently, there must be a force that is holding the water together and also on the surface of the coin. The force holding the water together is called cohesive, while the one holding the water onto the surface of the coin is called adhesive. Cohesive force is the force of attraction between molecules of the same kind, for example water and water molecules. Adhesive force is the force of attraction between molecules of different kinds, for example water and metal. The two forces are responsible for the rising of liquids through capillary tubes. The liquid molecules stick to each other and also to the wall of the capillary tube. When the cohesive force is less than the adhesive force, the liquid forms a concave meniscus, for example in water. And when the cohesive force is greater than the adhesive force, the liquid forms a convex meniscus, like in mercury. Next, force of friction. Now, let's go back to our ball. We said the ball starts to move once an external force is applied to introduce an imbalance of forces. However, the ball doesn't move forever. It gradually decreases in speed and finally comes to a stop. Obviously, with all these forces acting on the ball, there must be another force that came into play to cause the ball to stop. This force is called friction. While the force applied is moving to the right, the force of friction is moving to the left. If there was no friction, the ball will roll forever at the same speed, with the only two forces being balanced. Interestingly, friction is a self-adjusting force. Consider a table standing on the floor. When you try to push it gently, it doesn't move. The frictional force opposes the motion. When you increase the pushing force, still the table doesn't move. And this shows that the force of friction increases as well. Friction always adjusts itself equal to the applied force up to a certain value called the limiting friction. Once the applied force surpasses this value, the object starts to move. Friction occurs due to irregularities on the surfaces of the two objects, which causes a kind of an interlock. Consider this wooden block lying on top of another. Although the plane is inclined, the small block doesn't slide over. And that is because the force of friction opposes any attempt to move. The force of friction that exists between two surfaces in contact when there is no relative motion is called static friction. When a force is applied, the block starts to slide. The friction that exists between two surfaces when one slides over the other is called sliding friction. If the object rolls on the surface, then the friction existing between the two surfaces is called rolling friction. Friction is advantageous because it allows us to be able to walk on the ground without sliding. Hammering nails into a wall and also braking of motor vehicles. However, because of friction between moving parts, it causes wear and tear and also reduces the efficiency of machines. It causes damages to vehicle tires and soles of shoes. Friction can be reduced in a number of ways. For example, oiling or greasing the moving parts of a machine. These lubricants form a thin film between the moving parts and fill the tiny pores and depressions on the surfaces. Because rolling friction is less than sliding friction, ball bearings and roller bearings are used for decreasing friction. Friction also occurs in liquids. An object sinks slowly in a viscous liquid due to the friction between the object and the liquid. Even objects falling through air experience friction with the air molecules. This friction between objects and fluids, that is liquids and gases, is called drag. Next is magnetic force. Now, consider a bar magnet on your screen. When we bring it closer to an iron nail, at some point the nail moves towards the magnet and sticks to it. It remains there until we manually separate them. This happens because there is a force of attraction that binds the magnet and the nail. This force is applied on the nail by the magnet, and hence it's called a magnetic force. Notice that the magnetic force takes effect on the nail even before they are in contact. This means the magnetic force exists around the magnet up to a certain distance from it. We call this region the magnetic field. The magnetic field is stronger closer to the magnet and decreases farther away. When any ferromagnetic material is within this field, it experiences the magnetic force. When two like poles of magnets are brought close together, there is a repulsive force. And when unlike poles are brought together, there is an attractive force. So unlike poles attract, and like poles repel one another. Electrostatic force. Consider rubbing a balloon on your hair. You will see the balloon will then start attracting your hair. If two balloons are rubbed on your hair, they will repel each other. This occurs because of electric charges which are displaced by rubbing together of the two materials. There are two types of electric charges, positive and negative. When you rub the balloon on your hair, the hair acquires positive charges and the balloon gathers negative charges. Like magnetic poles, opposite charges will attract one another, which is why the hair sticks to the balloon, and like charges repel, which is why the two balloons push each other away. Just like magnets, charges have electric fields around them, and this is the region around the charge where the electrostatic force can be felt. Next, centripetal force. Consider a small piece of stone tied to a string about 1 meter long. If you hold the string on one end and swing it in a circular path, two things will happen. You will feel the stone exert some force on your hand, trying to pull itself away. Secondly, you will have to constantly exert an equal and opposite force in order to keep the stone in its circular path. The force exerted by your hand to maintain the motion is called centripetal force. And therefore, centripetal force is a force that constrains a body to move in a circular path. it is directed towards the center of the circular path. Next, surface tension. Now, you may have observed a nail floating on water or an insect walking on water. How is it possible for a nail which is denser than water to float, and also for an insect to be able to walk on water? It is because the surface of water at rest behaves like a stretched elastic membrane supporting the needle and the insect. This property of liquids is called surface tension. So, surface tension is a force that causes the surface of a liquid to behave like a stretched elastic skin or membrane. Let's look at the molecular explanation of surface tension. Consider three molecules A, B, and C of a liquid. The dotted circle around each molecule represents the sphere of action of each molecule. The sphere of action of A is completely inside the liquid. It is attracted equally in all directions by the other molecules. There is no resultant force acting on the molecule A. The molecule B also does not experience any resultant force. A part of the sphere of action of C is above the liquid surface. The molecule C experiences a resultant downward force. Now consider molecule D lying on the liquid surface. This molecule has its sphere of action exactly half outside and half inside the liquid. The molecule therefore experiences a downward attractive force. Due to this downward force, the molecules on the surface experience a tension called surface tension. If you take a camel brush and dip it in water, its bristles separate from each other. But when they come out, they cling together as the free surface of the water film tries to contract due to surface tension. When a circular wireframe is dipped in a soap solution, it forms a thin soap film. When we place a cotton thread on this film, it takes an irregular shape. When we prick the film within the loop, the film inside the loop disappears and the thread loop takes a circular shape. For any given perimeter, a circle has maximum area. Therefore, the soap film possesses minimum surface area. By adding oil in water, we reduce surface tension, so the mosquitoes' eggs and larvae cannot float but will sink. Surface tension is affected by impurities as well as temperature. Impurities like detergents lower surface tension by breaking the cohesive forces between the water molecules. When temperature rises, the kinetic energy of the molecules increase, the intermolecular forces weaken, and cohesive forces decrease, lowering the surface tension. Next, action and reaction. Now, consider a boy kicking a ball against the wall. Why does the ball bounce back every time it hits the wall? It looks like the wall is kicking the ball back. The speed of return of the ball also differs depending on the force of the kick on the ball. Indeed, the wall exerts a force on the ball to return it back to the boy. The force with which the ball hits the wall is called action force. The force that the wall exerts on the ball to return it back is called the reaction force. The two forces are equal but oppositely directed. It happens everywhere. When you try pushing a wall, the wall applies an equal reaction force and pushes you back. And so, when one object exerts a force on another, the second object instantaneously exerts a force back on the first. The two forces are always equal in size or magnitude, but opposite in direction. These forces act on different objects, but never on the same object. And therefore, if we push an object, it pushes us back. And if we pull it, it pulls us back with a force of equal magnitude. In other words, for every action, there is an equal but opposite reaction. In the case of the boy, the action force is acted on the wall by the ball. The reaction force is acted on the ball by the wall. We can verify this using two spring balances. A is fixed on the wall with the other end hooked to spring balance B. When a force is applied on spring balance B, it also stretches spring balance A. Observe that the readings on A and B are the same, indicating equal magnitudes of forces on the springs. However, the direction of stretch of A is opposite that of B. As you pull B, its spring stretches due to the applied force. And since A and B are hooked to each other, B applies the force on A, stretching the spring therein. A therefore reacts to the pull by B with the same amount of force. Now, let's look at two quantities, mass and weight. We have already defined mass as the quantity of matter in an object and that it is measured in kilograms. We've also said that any two objects that have mass experience a force or a pull of gravity. Weight is that pull of gravity on an object. Consider two objects, one of them being the earth. Because both of them have masses, then they pull each other. That force with which the earth is pulling the object will be the weight of the object on earth. It has been shown that for every 1 kilogram mass of an object, the earth exerts a gravitational pull or force of 9.8 newtons. This is written as G equals to 9.8 newtons per kilogram. So to calculate the weight W of an object of mass M, we simply do weight is equal to M times G. And so if an object has a mass of 1 kilogram, it will have a weight of 9.8 newtons. Now, whereas the mass of an object does not change from place to place, weight does change. And that is because the force of gravity is different from place to place. Consider the same object now on the moon's surface. It is known that the moon's gravity is 1.6 newtons per kilogram, meaning that for every 1 kilogram, the moon exerts a force of 1.62 newtons. And therefore, an object of mass 1 kilogram will weigh 1.6 newtons on the moon's surface. Finally, scalar and vector quantities. Now, suppose someone tells you that there is a port 50 kilometers from your home. How long will it take you to find it? I doubt you ever will. And that is because the person has given you the distance, but the question is 50 kilometers in what direction? It could be this, that, or that. The person has only provided the size or magnitude of the distance. Quantities that have only magnitude but no direction are called scalar quantities. Magnitude simply means the size of something. For example, 50 kilograms is the magnitude of mass, 3 hours is the magnitude of time, 4.8 newtons is the magnitude of force, 25 Kelvin is the magnitude of temperature, and so on and so on. If your friend says 50 kilometers northeast, then you have all the information on the precise location of the item. This is now a two-dimensional information. It has both magnitude, 50 kilometers, and direction, northeast. This now becomes displacement. Quantities like displacement that have both magnitude and direction are called vector quantities. Speed is an example of a scalar quantity, indicating only the magnitude, but not specifying any direction. In velocity, however, the magnitude and direction are indicated, making it a vector quantity. When you add the direction factor to speed, it becomes velocity. Weight is a vector quantity. It has both magnitude and direction towards the center of the earth. Mass is a scalar quantity. All vector quantities obey a special rule for addition and subtraction, which takes into account the direction as well as magnitude. The sum of two or more vectors is the resultant vector. Consider a person pushing a block with a force of 100 newtons and another person pushing it with a force of 60 newtons. The resultant force will be 100 plus 60, which is 160 newtons towards the right. What if the 60 newton force now pushes from the opposite direction? The resultant force will be the difference between them. If you take the left to right direction to be positive and the right to left direction to be negative, then the resultant force will be 100 minus 60, which is 40 newtons towards the right.